Log on, tune in, find out. Another good idea from Cambridge.
To introduce Elisabetta Itz from Indianapolis, who will talk on Riemann-Hilbert approach to scattering problems in elastic media. This is in our continuing Tuesday seminar series.
You have to
Where? Here?
Yeah.
Could I put it here?
Yeah.
I'm so scared of this stuff. It always stops working when I touch it. Just touch it. All right. So I'm going to talk about Riemann-Hilbert approach to the elastodynamic equation. And this is a joint work with Alexander and with Julius Kaplunov of Brunel University, London. And first of all, I would like to give you some little bit of history of this project. One of the traditional methods for studying elastic wave scattering in the medias with two or more perpendicular or near perpendicular interfaces is based on the green function technique. It was developed for computing reflection and refraction coefficients of elastic surface wave at various models of deep fault zones. Models like, well, just the simple model like that, just an interface, or it could be kind of, fancy shape, or it could be a bench of interfaces. This method, it contains some approximations, and over a period of time, we significantly improved the quality of these approximations, but one thing did not change. Every time when we had to write a green function in a quarter space, we had to actually write the formulas for the space, half space, not for the quarter space. And the reason is very simple, because the elastodynamic equation has not been solved exactly analytically in a quarter space. And it was a very long standing dream that might be someday we would be able to solve the elastodynamic equation in a quarter space, and we would get some at least simple test problems for our technique. Meanwhile, there was a dramatic development in the theory of integrable system. In particular, the inverse scattering transform method was developed. It was recently outlined here during the workshop in the lecture of Ludwig Faddeev. And gradually, the inverse scattering transform method was transferred, was kind of developed into what we now know the Riemann-Hilbert approach for the Cauchy problem for integrable PDEs. And in the end of 90s, Thanasis Focus came up with an idea. First of all, he developed a kind of a new version of this method for initial boundary problems. And he came up with the idea that it was possible to use this method not only for nonlinear integrable PDEs, but also for boundary problems for linear PDEs. And then, well, I personally became very excited because it seemed that we had now a possibility to solve the elastodynamic equation in the quarter space. And Alexander trained me in complex analysis, and we started this project. And first, I want to remind you the basic ideas of focus method. Suppose we want to solve the linear PDE with some boundary conditions. Instead of solving it directly, we switch to the system of two ODEs for some auxiliary function phi. K here is a complex spectral parameter, and the compatibility condition for this auxiliary scalar function is equivalent to the original ODE PDE. Then, solving this system of ODEs, we can single out some particular solutions which are analytic on certain regions of the complex plane K, except the oriented contour K. And on the contour K, we can write the difference. Between the solutions in the region. And of course, this difference is the solution of the homogeneous ODE. So we come up with this Riemann-Hilbert problem. And it should hold for all x and y's. So we, in particular, can use it for those x and y's which are included in the boundary conditions. And in that way, we could hopefully express the jump function rho, which plays in this solution, of course, kind of a role of, constant of coefficient of integration, we might say, and we could express it in terms of the given boundary data. If so, then the solution for the auxiliary function could be presented via the Cauchy integral, and then using some asymptotic relation, asymptotes for the phi, we could go back to the solution for the original unknown function. That's the idea. Of course, the most difficult step here is how to find the jump function.
So the PDE is constant coefficient?
Yeah, it's constant coefficients. Like the elastodynamic equation. Okay, I will tell in a second. So now, let's see how it could be applied for the elastodynamic equation. You see, we are working in 2D, and you see the elastodynamic equation in the media, which is described by the Lamé parameters. They are constants, and the density rho. And we are working in the frequency domain. The equation can be rewritten, or I forgot to say, sorry. I forgot to say that, of course, we want to solve for the displacement x and z components of the displacement.
This is not the same row as before.
Hmm?
This is not the same row as before, right?
No, it's not the same, sorry. It's just a density. It's so we can rewrite the elastodynamic equation in this vector form, which is convenient for application of focus scheme, because in his scheme the PDE should be a first order PDE with respect to one variable. So we decrease the order of the equation, increasing the number of the unknowns. And the equation should be solved for, well, we are going to solve it for the stress-free boundary conditions on z equals 0 and on x equals 0. So we are just solving in a quarter space z x. And the right-hand side parts of the boundary conditions, they could be, for example, interpreted as the stresses in the incident, say, Rayleigh waves. The solution also, of course, should satisfy the near-field radiation condition. And now we start our work. First, because the equation is the linear equation, there is a simple way, which was shown by Thanasis, how to write the Lux pair. Lux pair is, again, I forgot to mention that, it was the system of those linear ODEs, which I described before. So we write the Lux pair in this way, and then in this case, our Lux pair is a matrix Lux pair, and we have a matrix auxiliary function. And then we start working with this Lux pair using the first equation to get rid of the derivatives with respect to this, substituting into the second. We come up with the representation for the Lux pair, which already reminds, I hope you, the Lux pair in Thanasis scheme. And then there are some simple tricks how to work with this Lux pair. We start first diagonalization, normalization, and then uniformization. And as a result, this matrix Lux pair is split into 4 scalar Lux pairs, but only 2 of them are really independent. This part of the work, in a sense, is absolutely, not absolutely, but equivalent to separation of variables in the elastodynamic equation. Everybody who had to work with the elastodynamic equation knows that the equation itself in the homogeneous elastic space, it's not a problem. It is possible to separate variables in the equation. What does not allow us to solve the equation, it's the boundary conditions which link the separated Helmholtz equation if you separate the elastodynamic equation. And exactly like the equation itself could be separated and could be written as a couple of Helmholtz type of equations, in the same way, the Lux pair, matrix Lux pair, could be split into scalar Lux pairs, and this scalar Lux pair, they are Helmholtz type Lux pairs. This Lux pair, first independent Lux pair, it is written in terms of already a scalar auxiliary function phi, and because it is we did already uniformization, it is given in terms of a different complex spectral parameter, zeta. Moreover, exactly like when you separate the variables in the elastodynamic equation, you switch to some potential functions, which are the combinations of the original displacement. In exactly the same way, here we are switching to some combination of the unknown displacement to the function tau. The auxiliary function here is already properly decaying, and we have the asymptotic equations for it. And the second equation will allow us, if we find the solution for the auxiliary function, it will allow us to go back to find the solution for tau. In a similar way, the second Lax pair can be written in a similar form, but for a slightly different potential function tau, and it could be written on its own zeta tilde complex plane. In terms of this potential functions tau1 and tau2, the Sommerfeld radiation condition is presented on this slide. Now, before I actually start talking about the quarter space, I will describe all steps of the solution for the problem, which could be solved either by Laplace or by Fourier transform, which is not a difficult problem, the elastodynamic equation in the half space. So it means for a while I'm dropping one set of the boundary conditions, and we are solving the problem only with the boundary conditions for zeta equals for z equals 0. So the Lax pair is prepared for integration. It is written as a complete differential, and we write the solution as this line integral. Now, what we need to fill the complex space with analytic partial solutions. And in this case, it is enough to choose two contours of integration and to get just two partial solutions, and they are analytic in the marked regions of the complex plane. And you see, everything is filled. On the border of those regions, that is on the contour K, we now can start writing the difference between the solutions from the right from the left. It means start writing the jump equation. So that's the jump equation, and it should hold for all z and x's, and we have to write it for those z's which are included into the boundary condition, and we hope to get rho in terms of the given boundary data. If we manage to do so, then the solution is presented as this Cauchy integral, and we go back using that asymptotic equation which I mentioned before, and can write the solution for tau. All right, now let's start expressing the jump function rho. We have, in this case, just one jump function, rho 1, 2, in terms of the boundary data. Well, we write the integral, then we substitute the boundary data, we do some simple tricks like integration by parts, and as a result, we only partially can actually achieve our goal. We express the jump function in terms of the known boundary data and in terms of two unknown functions which are given by these integrals and which include the displacements on the boundary, the x component and z components of the displacement, which cannot be expressed in terms of the boundary data. So now I will describe the additional element of focus scheme, which will help us to find these functions. This element is called the global relation. So again, we rewrite the jump function as the integral, and we rewrite it as the line integral of the conservative vector field. And then for the parts of the contour, so this part and that part of the contour, it is not difficult to show that the contour of integration could be closed in the upper plane. So because of the strong exponential decay here, we have 0 on this closed part. It means we have 0 for the jump function on these parts of contour K. And this equation, rho 1, 2 equals 0 for this part of the contours, it constitutes the global relation for our problem. Okay, next picture. I was talking about this part of the contour. I have not mentioned this circular part of the contour K. And the global relation tells us nothing about this circular part. And for some while, it was a kind of a stopping point in this solution, because we just did not know what to do with the circular part of the contour. And then we realized that actually the Sommerfeld radiation condition plays more or less the same role for the circular part of the contour, and it will allow us to get the equation which is equivalent to the global relation for this part. Now let's see how it happens. So we just rewrite the tau 1 again as the integral and apply the stationary phase estimate to it. And it appeared that there are two stationary phase points, and they belong to the left and to the right parts of the circular contour. Moreover, the points, they give us the following asymptotic estimates for rho, and we see at once that the second one does not satisfy the radiation condition. It means on that part, left part of the contour, we have again a zero jump. But the point is that actually, so now we have kind of zero here and zero there. But what we need is the unknown functions here and there. That's why we use symmetries. Oh, here it's once again the expression for the jump and the global relation. On that slide, yeah, and what we are doing now, we are moving the global relation, the equation which relates the unknown functions from these parts and from these parts to the parts where we need them. So using this symmetry, and as a result, we obtained the equation relating the unknown functions on the parts of the contour which we need for the solution. In a similar way, it could be done for the circular part of the contour. So it means that now we have one equation relating two unknown functions on the contour where we need them. But still, it's of course not enough. However, we have the second Lax pair, and doing the same thing, similar thing, we could obtain a similar results. But of course, this second Lax pair, it is given on its own complex plane, zeta tilde. As a result, the unknown functions differ from the functions which we considered before, and this displacement are the same, but the exponents are different. So we got the second equation, but for different functions. And the idea now is to move everything to one complex plane. And doing that in the following way, we could now consider the exponents, we could change the exponents to the same exponent, which is done by the following map. And this map, the one for zeta and the new spectral parameter xc here and the second one here, allows us to fulfill this goal. As a result, the contours, they are changing. Of course, the first one is just rescaling, but for the second Lax pair, we have not only the rescaling, but also some parts of the circular contour, they kind of moved to the imaginary line, and we obtain this contour. However, still everything is fine. We know everything about all parts of these contours, and our unknown functions phi 1 and phi 1 tilde became phi 1 tilde of xc, and the same with second part. So we have now two equations, and we have two unknown functions, and we could solve this system of just algebraic equations, and we could obtain the unknown functions. And then going back to the original zeta and zeta tilde plane, we could find the jump which we want for the solution, and the solution is finished. Now, let's see how it could be applied now for the real problem for the quarter space. So we first do kind of the same. We write the auxiliary function for the first Lax pair is the line integral, but now it's not enough just 2 rays of integration. We have to use 3 rays of integration, and we obtain 3 partial solutions, and these partial solutions, they are analytic in the marked regions of the complex plane. And there are, now I want you to pay attention, there are 2 regions where we have 2 analytic solutions, and these regions, they will play a special role in the solution, because exactly in these regions we will set up the global relation, which, roughly speaking, is equivalent to the statement that the solution should be unique. And moreover, there is no jump here, there is no jump here, there is no jump on this part, there is no jump there. And we obtain the contour which looks like that, and the Riemann-Hilbert problem is presented by this equation. And if we manage to find the jump function, then everything is fine. However, when we start substituting the boundary conditions into the jump function, here I show you just one of the jump functions, rho 1, 3. There are 3 of them because there are 3 partial solutions. We obtain that the jump function is expressed in the boundary data, but also it includes 4 unknown functions. And now, compared to the previous problem, you could see in the previous problem we had only x exponents in the unknown functions. Now we have both x and z exponents. Well, probably before I describe this slide, let me go back for a second and talk about this picture. As I mentioned before, we will formulate the global relation in these regions. It's not like it used to be for the previous solution when we formulated the global relation exactly on the contour of integration. Now we have it in the regions, and it means that this part of the solution will be different, because instead of obtaining the equations as the global relation, we will have to set up the supplemental Riemann-Hilbert problem, moving the global relations from this region onto the whole complex plane. Actually, it became, after we did joint uniformization, not a complex plane, but a Riemann surface. And what is the idea of the joint uniformization? Exactly like before, we tried to make the unknown functions the same in the old and the new complex plane. Now we could try to make the functions for the first Lax pair and for the second Lax pair the same, but only for one set of the unknown functions. We make the same. The exponents the same, doing the joint uniformization, and the rest is different. So it means that instead of having 4 unknown functions for the one Lax pair and 4 unknown functions for the second Lax pair, on the joint Riemann surface, we obtained 6 unknown functions. So, as I mentioned before, we formulated the global relation for the first Lax pair, for the second Lax pair in the marked regions. And then, in a similar way as we did before, now we have to extend these global relations from the regions where they were formulated to the whole Riemann surface. So we do it using some symmetries, like that for global relation, and in the similar way we could work with the circular part of the contour using the radiation condition. And as a result, the whole Riemann surface is filled with the global relation and its extension. And on this picture you see the regions of analysticities of the unknown, 6 unknown functions. It's just one sheet of the Riemann surface. And now we are ready to start formulating the auxiliary Riemann problem for the unknown functions. Please take a look, for example, on the imaginary part. You see that phi1, phi2 unknown functions, they don't have any jump on this part of the contour. The same about their continuations. So the same here, the same here. It means that when we start writing the jump equation, for example, on this cross part of the contour, these 2 functions, they will be eliminated from the jump equation, and we will come up with the equations which will contain only 4 unknown functions. In the formal way, it is formulated on that slide. We are working already on the elliptic curve at torus, and we introduce the new auxiliary function with 4 components, and these 4 components, they are expressed in terms of 2 phi functions which we could not eliminate on the real line, and in terms of the psi functions. So it means that on this picture you see the Riemann surface, which the contours on the Riemann surface, which are divided in various parts, and I am showing you now the jump equation for one part of this contour. And you see it is now a vector Riemann-Hilbert problem formulated on this part of the contour, and unfortunately at once we see it is not well posed. It would have been well posed if, for example, instead of phi 1 we would have phi 3 here and phi 4 there, the same here. It would have been a normal matrix Riemann, vector Riemann-Hilbert problem, but as it is not. But let's now go back a little bit and recall what does these unknown functions mean. These two, we already got rid of them, so we are talking about these four unknown functions. And we see that actually these two, they depend on the same unknown kind of parameter, the displacement on the border. U displacement, and here these two, they depend only also on this same real unknown function. And what is different is just the exponents. And that means that one function can be rewritten in terms of another function, but shifted. And that's what we are doing next. Here we are. So we express one unknown function in terms of another unknown function, but with a shift which is given by the conformal map, and this map is presented on that picture, and that completes our setting of the supplemental Riemann-Hilbert problem is a well-defined vector Riemann-Hilbert problem with a shift. We achieved that goal. You see now we have only phi 3 and phi 4 unknown functions. And now we are working on the factoring this vector Riemann-Hilbert problem, and I hope in the future we will be able to present you the results. The results of this work are recently published in Letters in Mathematical Physics. That's the paper. Thank you.
Thank you very much. Questions?
You said quarter of space. You have what you mean quarter of plane, yes?
Plane, yes, plane. Quarter of plane, not space, yes. Maybe as a co-presenter, I can just 2-3 minutes some sort of remark. So I want to emphasize the key thing. So of course we have to solve a PD with constant coefficients. It is very easy to write, so this part of solution, this part of the formula is rather easy. So the fact that the solution is given as some contour integral with a proper dispersion relation RK and some contour. Because this is a sort of, that's the general formula for basically that any solution of PD of 1 plus 1 PD can be represented in this way. Of course, the question is, what about K and rho of K? How to relate them with the boundary, with the given boundary date? This is the whole thing. So, and the focus idea. So the idea is what the message of the focus method is that he suggests that this idea, which is borrowed from nonlinear soliton theory, is suggested to try to work to set some regular way how you can determine. So basically the contour K is not very difficult to guess, of course, just looking at this thing. But the most real problem, most serious problem is to determine this rho, because this rho involved extra. It is basically in your language it would be to determine Neumann to Dirichlet map. So this is what we're actually doing. So we try to find explicitly Neumann to Dirichlet map. We're given stresses. We want to find U. We want to find the Z. So on the bound, that's this whole thing. And it turns out that this scheme, focus scheme, it has this thing which is called global relation. It is a mechanism how you're supposed to do it. So as it is written, it is still transcendental problem itself. But we hope that again, for a lot of examples, it really can be still solved explicitly. For instance, in this simple example with the half plane, Elizabeth showed how it can be just solved algebraically, just confined algebraic cases. But for the more complicated situation, which is of course quarter space, the only things which we can now do, we can suggest an analytical problem which solves this. So this is a problem, this Riemann-Hilbert problem with the shift on the torus. It is a problem that equivalent to the Neumann to Dirichlet problem for this elastic equation. We have gained. So what now the last things? What is the reason for our optimism with doing with this problem? So it might be with doing with this problem. Well, it is just the experience which we gained for many years working in soliton theory and solving different challenging Riemann-Hilbert problems. That okay, we hope that we can really manage with this, but we might not. So this is it is a very challenging problem. So it's quite possible that there is no explicit solution. By explicit solution, I mean representation in terms of elliptic functions. So this is a finite goal, to solve this in terms of elliptic functions. It might be still not possible. So after all, it is a matrix problem posed on torus. It is matrix problem. You not always, even if there is no shift, you don't you cannot factorize explicitly. Okay, but thank you very much for agreeing to this.